All right. So a few more weeks and all of you will be engineers.
Crazy.
How does it feel?
Not ready.
Not ready. You want to study more?
I mean, it just seems like, well, the semester's ending earlier, which is weird. The fact that, like, next week's the last week of classes, right?
Yeah.
That's weird. I don't know.
So one more week and you'd be ready?
No. Let's be real. Is 1 week going to change anything?
Yeah.
But, it's scary.
Yeah, don't worry. They teach you everything on the job. And you know, if you miss school too much, you can always come back for grad school. Yeah. Yeah. All right. So I guess we're down to 2 now. Okay. You know, one of these days, I'd love to see people miss Dr. Boujon's class because they have to study for wave mechanics or they have to study for ship hydrodynamics. But that never happens. I wonder why. Okay. So last time we were talking about, okay, you know, we do small scale tests. How do we make sure the data we get works for the big actual ship? And we were talking about the method that True proposed, right? There were basically 4 different steps. Run the small scale model, make sure the Froude number is the same, measure the drag, subtract frictional resistance estimate. The remainder is wave making drag. And then we say the full size ship has the same wave making drag. And then we add back a frictional drag to the full size ship. Okay. And we'll do an example today where this will become very, very clear. So this procedure is followed by everybody in the shipbuilding industry today. There's, I assume you've heard of the ITTC? No? Okay, so it's the International Towing Tank Conference. They basically establish these procedures, so everybody follows the same set of procedures. Okay, so but you know, the reason we have to go through all this is because it's impossible to get the Reynolds number and the Froude number to match between the big ship and the tiny model simultaneously. So that's why we have this workaround. So keep this in mind that this approach is not, let's say, theoretically sound, but the values we get will be, they are good enough for practical purposes. So although Yeah, that's the best we can do. There's really no good workaround we know at the moment. Right, so let's do a few examples. Oh no, feet. Where did feet come from? Okay, fine. Okay, so full size ship, 435 feet, uh, which runs at 35 knots. We need to test a small scale model that's only 18 feet. What speed should we run it at? How do we figure this out? So you're saying we should match the Reynolds number for the two ships? In fluid mechanics, that's the first thing we would do. But with ships, we care more about the Froude number.
We're just trying to find the third number.
Is u over square root of GL.
Okay.
Yeah. So, ideally, we want to match both of them, but we cannot. So we start with matching the Froude number. Okay. So to do the testing, we need to make sure that we need the Froude number of the model to be the same as Froude number of the prototype. A Froude number is U divided by square root of G L. Okay, and unfortunately, we don't have meters per second because nautical speed, knots. But that's fine. We just keep track of all the units and we'll be fine. So G here, instead of meter per second squared, you would have to have knot plus divided by feet squared. So weird numbers. But we don't really care because the constants cancel out, right? So then we're left with UM. What is UM? All right, that's the thing we don't know. So is UM divided by, what is LM? Yeah, is the model, right? Small scale model. So it's 18 feet. And then here we have UP is 35 knots. And 435 feet. Okay, and when you do this, you'll get UM is about 7.12 knots. So we will need to run our small scale model at this speed in our towing tank. This is the opposite of what happens if you want to match the Reynolds number, right? A smaller thing going the same Reynolds number needs to move much faster. But here we have the opposite. This is why it's impossible to match the Froude and the Reynolds number simultaneously. Any questions? All right. So let's do another example where we talk about computing the drag for these towing tank experiments. So yeah, before we do the example, let me write out the steps with the formulas. So determining ship resistance. And the example we did, we just figured out, okay, we need to run it at this speed, but we didn't talk about what's the drag, right? How much power do we need for the full size ship? We didn't do any of those estimates. We would do that right now. Okay, so when you do the experiment, what is step one? So determining what the full size ship fruit number is and making sure we put the model in the towing tank at the same fruit number, right? So put M in towing tank. And flow speed adjusted to match fruit number. Right, that's your input to the experiment. What is the output from the experiment at step one? Measuring the total drag, correct? Yeah, measuring the total resistance. So measure total drag and use this value to compute CD for the model. Okay. And this CD for the model, well, I hope you all remember, it's just the force drag measured divided by half rho mu m squared sm, or this is usually lm squared. Once we have the value for this CD, we know it's composed of two different things. It's composed of the wave drag coefficient and the frictional drag coefficient. So this CDM is made of two things, the frictional drag coefficient for the model and the, let's call it CW, wave drag coefficient for the model. Okay, and at step one, this guy is what we're trying to retrieve, the CW, the wave drag coefficient. So the one we need is CW this is measured from towing tank. This guy is unknown, and we need an estimate for this.
The unknown is the coefficient of force, or is that an F? I don't know. I can't really.
Yeah, it's CF, frictional coefficient.
Oh, friction. Okay, I'm sorry.
Okay, so we measure the CD from our towing tank experiment, frictional drag coefficient. We don't know. We have to have some way of estimating it. And if we know these two, we can get the wave making drag coefficient. So this unknown guy, well, um, all right. So this committee, the ITTC committee, they compile data from many different experiments, and they found an empirical relation that gives us a good estimate for this unknown CF. So CF, which is defined as the frictional drag force divided by half rho u squared s wetted. They found that this empirical relation gives us a good estimate. If you notice in this formula, everything is a constant except for the Reynolds number. And the Reynolds number, since we know, well, do we know the Reynolds number? Why do you say we don't know the Reynolds number? What did you do in step 1? You made sure you run at the same crude number. Length cannot change. So you have determined what is the speed you need to run it at. If you're running it in salt water, you know the viscosity for salt water. If you're running it in freshwater tank, you plug in the viscosity for freshwater. Yeah, so the only variable in here is the RE. Okay. Then step 3. We computed the CF for the model. We will compute the CF for the full-size ship. And you notice that they will be different because the Reynolds number for the two ships is different for the full size versus the small model. So step 3 is compute. Now we have everything we need to compute the drag coefficient for the full size ship. Well, at least a good enough estimate. So that's the final step. What's the final step? What's the equation we should write? The drag coefficient for the full size ship is equal to what? Yeah, it's the CF for the prototype plus C wave making for the prototype. Do we know these two? What about the first one, CF? Do we know CF? Yeah, CF for the prototype is exactly what we computed here in step 3. CW for the prototype, that's why we had step 1, where this is step 1, where we computed CW for the model, and that's our, we say CW for the model is the same as CW for the prototype because they're running at the same Froude number. Okay, so this CFP computed in step 3. And for this guy, we assume So that's Trude's procedure. Why do we care so much? Why do we go through all this, all these steps? What is the end goal? Why is this useful? We have determined CD. What should we do with it?
Find the drag.
Find drag, which lets us do what? You know the drag force for a ship, how's that useful?
I guess you need it to compute your thrust force for your power supply.
And that helps you size your engine, right? It helps you figure out how much fuel you need to carry in order to get to your destination. You know, also, you know, if you know how much fuel you carry, you can determine where you store it, because we know it will affect stability. As the fuel drains out, you'll create a free surface, which will reduce your GM. So hopefully now you see everything ties together, everything that we've talked about. So Okay, let's do an example where all of this will become concrete. It's a long example, so I'll be writing for a while. Okay, are most people done writing? Okay, stop writing for a second and let's just take a quick look at the problem. Remember, never jump to using formulas, right? Set up the problem in your mind first. So we have an 80-meter long ship. We have a small scale model. Size, what size? What's the small scale model you're testing? 4 meters, yeah. 80-meter, 1 to 20 scale. We're given the towing tank speed of 3.5 knots. And we are told in the towing tank, we measure the drag to be 35 Newton. So this is basically step one data given to us. How do we use this information, the model information? Forget about the rest of the stuff for a second.
I guess we'll use that information to get the Froude number.
Exactly. So we know the length, we know the speed, we can get the Froude number of the model, and we know we have to do the estimate for the full-size ship at the same Froude number. So we can compute what speed the full-size ship would be going at, how many knots. Okay, then that's all of the top stuff done. Then we think about what's given here, all right? 15 degree, we don't really care about the temperature, but this affects density and viscosity. So we care about these things. Density, viscosity, what number do we always compute using these things, density and viscosity? Drag coefficient, not directly.
A Reynolds number.
The Reynolds number, the viscosity, right? That's needed to compute the Reynolds number. So this is a freshwater tank. We can compute the Reynolds number in the freshwater tank. And then we're given details for the ship operating in salt water. Again, we don't care about temperature. We care about viscosity density. We can compute the Reynolds number of the full-size ship. So you see, once we have the Reynolds number, we can compute CF for both of them independently. And once we have the CF, once we have the Froude matched, we know we can compute the total CD for the ship. Once you compute the total CD, you see we have the surface area, and we can compute the drag acting on the full ship. If we know the drag acting on the full ship, we can compute the power required for the full ship. So that's it. I mean, it's a long, there's many sentences, but always break it up in your head before you put pen to paper. Not just these problems, any problem. Okay, now computing the power required. Let me give you a few side notes before we delve into this example. And what is this roughness allowance that's mentioned? So How do you compute power?
The force times your velocity.
Yeah, if you remember, work done is what? Force times displacement. F dot S, force times the distance moved. So power is F dot U, force times velocity. So this is F drag times the speed you're moving at. That comes out in Newton, and if you, one very commonly used unit of power is horsepower. So this comes out in, not in Newton, Newton meter per second, right? Watt.
Watt, yeah.
And okay, so next thing I want to tell you about is this sentence, include roughness allowance to the ship resistance. What does this mean? So, you know, these towing tank experiments that we do, the small scale model is clean and the hull is not barnacles or other stuff. So we can include an additional allowance for this that will happen out in the field. We increase the drag coefficient slightly by adding a number. So sometimes Any questions before we start solving the example? Okay. All right, so I'll note down what's given to us. Length of the prototype is given. This is 80 meter. What about length of the model? It's 80 over 20, which is 4 meters. Model speed is given. U model is 3.5 knots, which is 1.8 meter per second. Then drag for the model is given, and so F drag for the model 35 Newton. Density for the model is given. Density for the water where model is tested is given 999. Viscosity is given. Oh, not mu. Prototype water density is given. Prototype viscosity is given. Then wetted surface area, so S E is given 1290 meters squared. Okay, that's everything that's given. So step one, what is step one? Where do we start with all this data that's given?
Determine the Froude number.
Determine the Froude number, make sure we match it between the prototype and the model, which will give us the unknown UP. We don't know the speed of the prototype yet. So fruit number is matched, what do we do next? Once fruit number is matched, what do we assume? What assumption does it allow matching the fruit number?
The wave resistance coefficients match.
Exactly. So once we have matched fruit number, the next assumption we can make is the coefficient, drag coefficient from wave resistance will match for the two. We need to find what that is. That's basically step 2 and 3. So step 2 is F drag for the model is given 35 Newton. So we'd compute CD for the model is 35 divided by half. Rho m u m squared sm rho m is 999, um is 1.8 times sm. What is sm? So you're saying we know SP, so we divide it by 20 to get the SM. Close. You do that when you're changing the length, right? 80 meters become 4 meters. Think about what would happen with the area. Correct. You divide the area of the full ship squared by 20 squared, and you get the area of the little guy. And this is perfectly analytical because it's geometrically similar. All you're doing is squishing down the area. Okay. So this is the wetted surface area. Wetted surface area, you understand what I mean? Is basically the hull that's wetted, right? What the water is touching against. And that changes with your waterline level, with your draft. Wetted surface area for model. Okay, and this guy we can compute as okay, and when you put that number in, we end up with the total drag coefficient is 6.71 e to the minus 3. What are the units?
Unitless. It's a coefficient.
Drag coefficient does not have any units, so non-dimensional unitless. Once we know the full CD, to get the wave drag, we do CW of the model is CD of the model minus CF of the model. To find this guy, we do step 3. Okay, what is, so we know the formula, the ITTC formula is 0.075 log base 10 RD model minus 2 whole squared. RE of the model we can compute. UM 1.8 poor. I've made a small mistake. I will fix it. I'll tell you what it is. Again, no units for the Reynolds number. We expect all the dimensions to cancel out. So what's the mistake I made? Let me bring back the, this is not mu, this is nu. Yeah, it was right the first time. Yeah, obviously the units, meter squared per second has to be nu. The mu has a kg in there, etc. So just fix this, these two. All right. So CFM, well, we've only figured out RE. Let's plug that in here to get CFM. What do we do with this CF model? Yeah, we need to find this guy. We have this from step one. We don't have this. We just computed this in, well, right now, right? So yeah, CW. I think I've mislabeled my steps, but it doesn't matter. I mean, this is the procedure we follow. Okay, next. We have the wave track for the model. And remember, since crude numbers are matched, we will say this is equal to wave track for the prototype. Okay, so we have one of the numbers we needed. Next step, we'll compute the CFP. Okay, this one's easy. We have REP, LP, UP, new P. Length is 80 meters. Speed is 8.05. New is without looking at the previous Reynolds number, what do you expect? This Reynolds number larger than the small scale model or bigger, smaller? Comparing the full prototype Reynolds number to the small scale model Reynolds number, what do we expect? This would be larger or smaller? Much, much, much larger, right? It's a full size model that's huge. So if you see, it's e to the 8, and the other guy was e to the 6. Model was e to the 6. So it's 100 times factor in terms of Reynolds number. And it can be much, much larger, the factor. Okay, so we have the Reynolds number. We plug that in here. So we get CFP. Yeah. 1.63 E minus 3. Okay, now we have CFP and we have CWP. So we can get total CD for prototype. CDP is what? Yeah, CFP plus CWP. We have those numbers above, so we get 5.08 E minus 3. And remember, this is, we haven't accounted for any paint damage or biofouling. So if the problem says do account for it, then we'll add the allowance here. That's the full drag coefficient, wave drag, frictional drag, and this extra allowance for biofouling. What next? Yeah, we can compute force from drag force, and then we can compute power. Okay, you just plug in the numbers, you'll get 234,708 Newton. Okay, so much larger for the real ship compared to our small 35 Newton for the small model. And power, you get roughly 2 megawatt, which is 2,534 horsepower. Does this seem unreasonable, 2,000 horsepower? It's a big ship. Have you ever encountered these numbers? Let's say your car. You know how much horsepower your car engine is on average? Ooh, 400. No, that's a very nice car. So my Honda Civic is 150 horsepower. Okay. Yeah, aircraft carrier would be even higher than this. This is for a destroyer, right? So, but I mean, if you think about the big muscle cars like the Ford Shelby GT 350 or 500, they go up to 800 horsepower. Okay, so you know, this is not an extraordinarily large number. Okay, any questions? So next time you study senior design, you'd be able to do these towing tank experiments when designing your own. Yeah, okay. Yeah, so this is a procedure you follow for any designing any surface going marine vessel. Okay. Don't forget about quiz on Wednesday. We'll cover material from homework 5.
This would have been really good to know, like last year.
Yeah, that's why exit interview, you tell them that we need to shift this to.
It should be right after, like, I don't know, like maybe spring last year. Like, what the hell?
Yeah,
It's like I got cheated.
I'm trying to get them to exchange wave mechanics and this ship hydrodynamics. No, I'm going to have that changed. Fluid
Yeah.
mechanics should be the prereq for this, and wave mechanics can come in the last term.
Yeah, like waves could have definitely been this semester, and it would have probably made more sense. You're 100% right.
Me saying these things matters much less than you all telling the department chair these things, right? So
I'll speak to him when I get a chance, because yeah, that's very, like, this would have been really great for us building. Like, man, I don't know. I'm not gonna keep complaining, but this would have been great.
no, please do complain so we can fix it for future students. So your complaining is good for the future generation.
No, I just meant like on here. I won't keep complaining, but I'll definitely tell Danik when I get a chance that this would have been useful.
Yeah. Okay, guys. So we're out of time. So I'll see you Wednesday, and don't forget about quiz.
Thank you. Have a good one, man. Bye.